Hi guys, this is a quick video recording to help you cover the first part of system software, that is Unit 5, Part 1 of the Cambridge 961 AS Level Computer Science syllabus. In this video or this lesson, we'll be covering operating systems, followed by what tasks an operating system does, the different operations of an operating system, stuff like memory management, process management, etc. And then we'll be looking at utility programs. What are the different kinds of utility programs we have, and what are their major tasks? What are the different purposes of the utility programs that we have? So without further ado, let's begin. The first topic being operating systems. Right now, before we get into operating systems as well as utility programs, it's important that I help you understand all the different parts of a computer system in terms of its hardware and its software. So I'm going to draw a quick diagram, and I think you guys might be able to also see in very uh, difficult to read, very light font. There are a bunch of items written here: user, application, software, other system software. So these are all the parts of a system, that make up an entire computer system, specifically a modern computer system, right? These are all the parts that make up a modern computer system. And what this diagram that I'm going to draw will help you understand is how each of these components work with each other and how they are connected, roughly speaking. Now, if you already know this, I would encourage you to give an attempt at drawing a small diagram connecting all these components up. The user, the application software, the other system software, blah, blah, blah. Try to connect them up and see if you can draw a diagram to roughly show how all of these things work together. Or you might have to draw arrows to show how these components are connected. But no, if you don't know how they are connected, there's no problem. I'll be showing it to you. But if you do, pause this video now, try to draw how these things are connected by yourself, and then you can, of course, unpause and take a look at whether your answer compares well with mine, or if there are any discrepancies or any other differences. But feel free to pause the video now and draw a diagram by yourself. Cool. So hopefully you guys were able to pause the video and draw a diagram, but if you weren't, that's also fine. Let me show you how all these components in a computer system, in a modern computer system, connect with each other or how they interact. Now, the first component of a system is a user. When I say component, it's not to say that the user comes with the machine. It's you. A user is what initiates the operations on a computer. Now, the user usually interacts with application software. With application software. Right? The user usually interacts with application software, where the user can engage with application software and the application software can respond to those user actions. And then the application software, let me give you an example as well. Could be, for example, a word processor, right? Could be a word processor like Microsoft Word, right? An application software is a software that provides a specific purpose to the user, a specific job. So a word processor's job is not to create spreadsheets or presentations, but to create documents. It's to edit, create Word documents. Now, these application softwares then interact with the operating system. Operating system. Now, what this operating system is, I'll explain to you in a bit, because it only makes sense once we draw the entire diagram to see what the definition of an operating system is. But then the software has to eventually be loaded into the RAM and it has to run with the help of the CPU, and it has to access files on the disk. So eventually this application software has to access the hardware, isn't it? Now, the application software directly has no connection to hardware, but the way it is able to interact and talk to the hardware is by the application software speaking to the operating system. The operating system then giving commands to these so-called device drivers, and these device drivers speaking to the hardware on behalf of the operating system, right? So hardware includes stuff like the RAM, the CPU, and even things like printers. Now, some core hardware components, the OS is able to directly manage without the use of device drivers. So you can imagine that there is the ability for the OS to directly manage hardware like the CPU and the RAM without the need of device drivers. But device drivers are most often relevant, especially when it comes to peripherals like printers and even things like displays and keyboards and mice. Most peripherals require device drivers, whereas built-in hardware, stuff on your motherboard, RAM, CPU, they may be directly controlled without the requirement of a device driver. But that's the overall process. Now, we do have a few branches in this diagram. This is not just a top to bottom pipeline. There are a few branches. Now, one major branch, and really the only branch that we discuss about in AS level, is this branch from the operating system to other system software. Now, what system software exactly is, I'll explain to you as well. But when we say other system software, it's important that we understand what system software is, because it feels like we are referring to something that has already been discussed, right? That's what other means. We have already discussed what the opposite of other is. We have already discussed what system software is made up of. And now we are discussing about something excluding what we've already discussed. But frankly, we haven't discussed anything about system software, isn't it? Now, therefore, let me just give you a quick introduction to what system software's components are, although I won't define it immediately. I'll give you an idea of what the components of system software is, so that way we know, okay, what doesn't fall into other system software. System software in this diagram is essentially a combination of the so-called other system software as well as device drivers, as well as the operating system. This section in total is what we refer to as system software, right? It's this section in total, other system software, operating systems, and device drivers, that we refer to as system software. So in reality, other system software is just system software, but without the operating system and device drivers. Hopefully that makes sense to you. And what are the different things that fall into other system software? We have translation software that we look at in the second part of Unit 5, Unit 5.2. Translation software. Then we have utility software, also known as utility programs. But that's mainly it, right? Those are the main components of system software that categorizes into other system software. We have translation software and utility programs. So in other words, system software is composed of the operating system, device drivers, translation software, and utility programs, essentially completing all the different parts of system software. Now that we understand what system software is composed of, and therefore what other system software mean, it's basically everything but the operating system and device drivers, we are ready to understand formal definitions for these things. And before I get to the formal definitions, actually, let me give you a few examples of operating systems, translation software, editing programs, and whatnot. So, of course, the user is you, right? User could be whatever your name is. Application software is, for example, the word processor. Operating system could be, for example, Microsoft Windows. Windows 11, let's say. And then device drivers could be, for example, like a printer drive. Without the printer driver, you can't print anything on the printer. Oops, sorry, that was a small presentation issue, but I'm back on the normal slide now. The printer driver could be an example of device driver. And then an example of a translation software could be, for example, a compiler. And an example of a utility program could be, for example, a disk defragmentation software, right? An example of a utility program could be defragmentation software, which we will look at in this lesson, right? So now I've given you examples, I've given you all the components and how they connect. Now you know the overall system architecture, right? As a result, I can now tell you what these so-called things are and what these things do. Application software are software that perform a specific task for the user. Performs a specific user task, right? Oops, there seems to be a small problem. The presentation seems to be jumping everything every single time I write, but sorry about that. Application software perform a specific user task. Then other system software, translation software will be studying about what that exactly is. But in summary, translation software is used to translate high-level programs into machine code. Utility programs, they are programs that perform the configuration and maintenance tasks of your computer, right? They look after your computer, just making sure that everything is running properly. So we'll look at the definition there as well soon. Operating systems. Operating systems, based on this diagram, can be thought of as a bridge between application software and the hardware via the device drivers. And that's exactly what operating systems are. Operating systems can be thought of as system software right, that act as a bridge between the application software and the hardware. That act as a bridge between apps and hardware, right? That act as a bridge between apps and hardware. Which is why I said that if you look at this entire diagram first and then look at the operating system's definition, that makes a lot more sense. It's literally something in between application software and hardware, where device drivers is something that translates the operating system's instructions to the hardware. But do keep in mind the device drivers aren't always necessary unless you're working with peripherals. If you're working with stuff like the RAM and the CPU, which are core system components built into your motherboard, then the operating system is able to talk to them directly. So the device drivers are kind of optional here, but the application software and the hardware is bridged together by the operating system. And as a result, the system software overall are all the different tools, softwares, and utilities that help control and manage the hardware, right? The system software is a name given to the suite of software that control the system. So in the entire hardware that manage all the hardware and also control them and also delegate resources to different applications based on requirement, based on priority, and a lot of different things, right? So system software is like a sort of like an umbrella term for all these things: translation software, utility programs, operating systems, and device drivers. But this serves as a foundation for understanding exactly how the system is composed of, which makes us ready to look at operating systems in detailed form now. Hopefully this may make sense to you guys. If you have any doubts, do let me know. Now, what exactly does the operating system do now? Like we discussed, an operating system is system software, right? And what does this system software do? It provides a software platform for applications and users, right? And as a result, it manages low-level hardware, right? specifically the low-level hardware operations, such as that of the RAM and the CPU, and exposes high-level APIs to developers. Allows developers to manage those low-level hardwares without having to work with the binary level stuff, right? API stands for Application Programming Interface. Right? Application Programming Interface is what API stands for. So the operating system provides an interface for developers to program the so-called underlying hardware features like the RAM and the CPU and whatnot. In essence, you could also summarize the OS's operation, like I said, as a bridge between the apps and the hardware, right? You could think of the operating system acting as a bridge between the hardware and the apps. But what we're discussing here in the points on the slide can be thought of as a more technical definition of an operating system. It's full form, which is helpful if you're writing a 4-marker or a 5-marker answer for what an operating system is. And it ensures controlled and fair access to CPU, memory, input, output, and storage by applications. So you can think of it as the democratic leader of sorts that gives all applications equal chance, depending on priority and depending on requirements to all applications. So for example, it makes sure that when you're running Google Chrome and the calculator on your computer, right? 2 applications. If you're running Google Chrome and the calculator, I'm referring to the calculator app on your computer, right? It ensures that the calculator app doesn't get like 16 GB of RAM when the operating system needs some memory to allocate to the Google Chrome application, right? Now, what are the different things that the OS does? The operating system does memory management. The operating system does file management. The operating system does memory management. The operating system does security management, as well as hardware management. Those are the 5 major tasks that the operating system does, which we will now discuss in detail. First up, memory management. Memory management of the operating system can be divided into 3 major tasks. First, we have memory organization, where you can think of this as the task responsible for managing the overall RAM, dividing memory into logical sections. Right? Dividing memory into logical sections. You can imagine that these logical sections are like blocks of the RAM that are dedicated for different tasks, but they have names that's specifically referred to as the stack, the heap, the code, and the data. Those are the different logical sections of memory. And you could use different techniques like paging and segmentation to organize the memory further. And there's also a specific name for paging and memory, paging memory systems and segmented memory systems. They are referred to as memory management systems used for converting or translating virtual or logical memory addresses into physical memory addresses. But that definition will only be looked at in A2. So you can imagine for all purposes at AS, it's just used for organizing memory. And it also maintains something called page tables and segmentation tables for performing address translation, which is exactly what I told you earlier, the whole concept of translating logical addresses into physical addresses in multitasking environments. Now, if you have multiple apps running in the same at the same time, and those multiple apps have to share the same RAM, the operating system takes care of making sure that all these applications have access to the RAM by performing address translation, such that no 2 applications share the same memories. And of course, we'll be looking at that in more detail under memory protection. So those are the things that are done under memory organization. Then we have memory optimization. Memory optimization is about using virtual memory to simulate more RAM using disk space, right? Ensures that all applications are given this illusion that they have unlimited RAM to use. Also, memory optimization involves a bit of caching to ensure that there's fast access for frequently accessed memory, as well as buffering to improve access speed. Then, like I said, memory protection ensures that each process is isolated to prevent unauthorized access of memory. So no two processors are ever expected to share the same memory addresses. And last but not least, memory protection involves some form of hardware level protection using these things called base limit registers and page level permissions to ensure that no two applications ever share the same memory locations, which will lead to crashes and also security vulnerabilities. So these are the three major things that memory management does. And you do need to know how to explain these three things in case you get a 4 mark or a 5 marker to answer about memory management. File management. This is quite simple. File management controls access to persistent storage using a kind of file system, right? It ensures that you are able to access your disk, store, read files, and of course, perform file operations like cut, copy, paste, etc. And file systems are of different names and types, but common examples that you find in a Windows operating system is FAT32 and NTFS. You can look at what these abbreviations stand for, but you don't need to understand anything about how they work. Although I will give you a quick introduction to it in a few slides from now. Then, file management is also about managing or handling metadata and ensuring hierarchical structures of folders and subfolders and subfolders and parent folders and child folders and all of that, right? And also file extensions, stuff like the .pdf being handled differently to .docx. The file management component of the OS is the one that's responsible for taking care of file extensions or file handlers. Then last but not least, access control lists, making sure that there are permissions of sorts and delegations for which users can access which files. And moving on from there, we have file permissions, like I just mentioned, which are for ensuring or permitting certain groups of users or per user the read, write, and execute rights for a file. And like I said, it enforces these file permissions for a user or for a group of users. Those are all the things that file management does. Security management. Security management takes care of two major things. It helps authenticate users using credentials such as passwords and authorization using permissions. It implements encryption, firewalls, and secure boot features. And it applies the principle of least privilege. What does this mean? This means that every user in the operating system is only given the least amount of privilege and nothing more. This prevents people from having elevated access to systems when they don't need to have elevated access, and they're only given access on a case-by-case basis. So principle of least privilege means any user or any accessor of this system is only given the least amount of privilege, and if they want more, they'll have to access it as a result, requiring passwords or some kind of elevated permission rights. And this allows to restrict user process actions beyond those permitted to it. And finally, it logs system of events for auditing purposes and to detect intruders. Hardware or I/O management controls hardware via device drivers. Device drivers can be thought of as modular software interfaces to hardware, which essentially convert and translate instructions from the operating system to a format that the hardware can understand. And it abstracts hardware details from applications via I/O APIs, input-output application programming interfaces. It doesn't let the applications worry about the actual hardware implementation details, right? It abstracts them away. And it manages things like interrupts, which we studied about in detail, and I/O scheduling, which is basically ensuring that different input-output devices have the ability to schedule how data is read or written to them based on priority and based on some kind of metric. So, for example, when you're reading and writing data from disks, the kind of scheduling algorithms you could use is FCFS, which is first come, first serve, or shortest seek time first. So, depending on the incoming request, whether you're using FCFS or shortest seek time first, SSTF, can determine which incoming read-write operations are read or written first. So first come, first serve means whichever disk operation comes first, that's the one that's read or written first. And then SSTF means whatever read operation has the shortest seek time, or with whatever read or write operation has the shortest seek time, that's the one that's done first. So depending on some kind of priority metric, you can schedule incoming and outgoing processors to an IO device. By the way, for those of you that heard the word seek time that I described, seek time is a time taken for a hard disk drive read-write head to find the correct block or sector in a file or in a hard disk drive, in a hard disk drive platter where the respective data is stored. And hardware management involves the use of buffers and spooling to handle device speed mismatches, right? That's pretty clear as well. Process management, last one. It does two major things, process scheduling and process control, where process scheduling is just like how we talked about scheduling for incoming processors into a hard disk drive. In CPUs, they perform a similar scheduling to ensure that CPU time is allocated to processors based on some kind of metric, whether it's based on the arrival time or whether it's based on how much time it takes to execute. That depends on the algorithm. So there are different algorithms for allocating CPU time, like round robin, first come, first serve, and some kind of priority scheduling system. And it uses a scheduler to decide which process runs next. And it maintains a ready queue for processors that are waiting for CPU time, waiting queue for processors that are blocked in some way as a result of an IO operation. And it supports context switching, which is basically the ability for processors to be removed from the CPU prematurely as a result of an interrupt or as a result of a more higher priority process coming in. And, after that is done, you can take back that process and continue execution without having to restart. That's what context switching means. Process control can be done using a process control block, which is another task performed by the process management section of the OS, which ensures that each processor's state, registers, and priority are kept persistently as long as the process is still executing. And it supports process creation, suspension, and termination. And it enables multitasking and tracks process life cycles. So whether they are new, whether they are ready, whether they are running, whether they are waiting, or whether they are terminated. Of course, this will be studied in great detail at A2 level. But up until now, this is all you need to know at face value what process management is. Now we move on into utility software. Now, utility software is software that is used to manage hardware. If I were to give you a definition for utility software, you could define utility software as system software that perform the maintenance and configuration tasks of the computer system, right? They are the guys that help computers keep running without failing or without being stale or without just, going up in flames. They don't really do anything that you might see. They are the literal underdogs of the system, you could imagine, that without the system would just crumble down. As a result, utility software are very important, although they don't perform a visual thing that you can see or happen every day. They do a lot of underlying underground tasks that you don't usually take into account on a day-to-day process, right? On a day-to-day use of a computer, you don't see them happen, but they do happen in the background. So system software that perform the maintenance and configuration tasks of the computer system are what we define as utility software. Now, the first kind of utility software that we have in our syllabus is the disk formatter, where the disk formatter software is there to prepare a storage device, such as an HDD or a hard disk drive. HDD is a hard disk drive, or a solid state drive, or a USB, by permanently erasing data that is already existing on the storage device and setting up a file system. So it's there to prepare storage devices for initial use or to repurpose a hardware device that was already previously used by permanently erasing existing data and setting up a new file system. Now, we talked about file system twice, once here and then earlier in file management. What is a file system? Now, a file system is essentially how the files in your computer are spread out, right? How are the files in your computer allocated? Now, one common way that files are allocated or stored on a disk is using a file system known as FAT, File Allocation Table. Now, you need not understand how file allocation tables work, but I'm going to explain it to you nonetheless, just because we mentioned it twice and it makes sense for you to understand what on earth a file system is. In a file allocation table computer or a disk, the idea is that if you consider a file, right, a file is made up of multiple blocks, right? For example, if you consider one of your Word documents, that Word document may be spread out into multiple blocks. So all these three blocks refer to a single docx file. So you see it as a single docx file, right? You see it as a single docx file, but it might be spread across multiple sectors on your hard disk drive, right? So this could be sector 1, this could be sector 2, and this could be sector 3. Or you can imagine them as block 1, 2, 3 as well. So once again, files are divided into blocks. Now, in order to find where each block is on the hard disk drive, you can use a file allocation table. In a file allocation table, the idea is there's first some kind of start pointer that tells us where in the hard disk drive is the first sector or the first block of your file store. So for example, if you look at file A, the fact that file A contains the start sector value 10 indicates that the first sector or the first block of file A is stored in address 10. And there you go. This yellow color section belongs to file A. That's the first block or the first sector of file A. And then that tells us the next block can be found at 3. There you go. And then that tells us the next block can be found at 12. And then the fact that there's a 0 here indicates that that's the end of the file. So you can imagine, right? You can use a file allocation table as a sort of a linked list to find where is your blocks of files stored. Right? That's a file allocation table. So that's essentially what setting up a file system means. It sets up a process through which blocks or sectors can be allocated. And like I said, right, setting up a file system ensures that block size and sector layout are defined to help ensure how organized the files are or how files are organized across the disk drive, right? And it enables the OS to manage file locations, directories, and access permissions as well. So that is what this formatter is used for. It's to permanently erase existing data, set up a file system, define block layout, sector layout, and manage operating system file locations, directories, and access permissions. And this formatting is all usually done when you buy a new disk from the shop, from the market, and you also do it when you have an old disk that you want to permanently wipe out and start from scratch. Then we have antivirus software. Antivirus software are there to scan files, memory, and boot sectors for malicious code. Antiviruses are softwares that help us get rid of viruses. What are viruses? Viruses are malicious software that essentially spread throughout the computer through a host application, a good application. So, they take or infiltrate a normal application on a computer, just like how a normal biological virus would. It would infiltrate one of our good cells and it'll use that to replicate and spread across our body, just like how a virus on the computer would replicate using the host application to other computers and other parts of your computer system in itself. But the way that antivirus software is able to detect viruses is using signature databases and using heuristic analysis. An example of a signature database is a very simple picture what you see on the right-hand side, where this is a database of already found viruses, already existing viruses that have been entered into a database which contains these so-called signatures, which are currently represented in hexadecimal here, but you can think of them as DNA of viruses, right? These are binary codes or binary instructions that these viruses would have if they were viruses, right? Now, these are the identifying binary code of these so-called viruses. So, for example, when a virus tries to run on your computer, the antivirus software would first check whether this software trying to run is one that has any of these binary codes inside it, any of these signatures. And if it has any of these signatures, it will directly flag it and maybe even quarantine it. Heuristic analysis is something else where there isn't a database check, but rather one that uses a bit of data analysis and machine learning to see whether the actions of a virus are kind of suspicious, right? Whether they're up to no good. So it's more of a behavioral check rather than a more strict database check. So those are the two ways that antivirus software do their job. And as a result of detecting a virus, it will quarantine, maybe delete, either automatically or use with your permission, or repair infected files to maintain system integrity. And it offers real-time protection and often has scheduled scanning for continuous threat monitoring as well. Defragmentation software. Now, as a result of continuous reading and writing operations on a hard disk drive, the data blocks of your file get fragmented or spread out across the disk. As you can see in this picture here, the file gets all over the place. All blocks of the file are desiccated across the hard disk drive. So defragmentation is to take all those fragmented blocks of a file and reorganize them. So that way data blocks are contiguous. So as a result, you'll end up cleaning up your hard disk drive so that all the files are now contiguous. You can access them from one place all the way to the end without having to have the read-write head move like a DJ. It's very easy to access the entire disk in one fine sweep without having the read-write head to undergo a seizure. So it reduces read-write head of movement. It reduces read-write head movement, improving access time and performance. But the problem with this is that it only works well for hard disk drives, because for SSDs, it doesn't really matter because SSDs have no moving parts. Fragmented files don't really slow down an SSD because SSDs are fast nonetheless. So SSDs don't need defragmentation. Since for SSDs, fragmentation does not impact performance. Since there are no moving parts, there are no read-write heads moving around. And it's actually discouraged from doing defragmentation on a SSD because you're significantly reducing its lifespan by performing a lot of read-write operations that don't really do anything purposeful, right? When you're defragmenting a hard disk drive, you're moving a lot of blocks from their existing locations to new locations. So you can imagine that compared to normal reader operations, throughout a defragmentation process, there is a very large number of reader operations that happen over a short time span. But on an SSD, when you do that kind of thing, when you overload the SSD with a lot of reader operations over a short period of time, you're actually prematurely killing the SSD from doing a lot of reader operations that don't really have any impact on what files you're reading or what kind of data that you're writing, right? Defragmentation is just rearrangement. You're not actually reading or writing data. As a result, you're wasting precious read-write cycles on an SSD on just rearranging, which frankly is not that important to an SSD because SSDs are fast nonetheless. They have no moving parts. So don't do defragmentation on an SSD because they're fast nonetheless. But SSDs, hard disk drives, absolutely, because it helps ensure that fragmented blocks are made contiguous, hence reducing the read-write head movement and therefore increasing access time. Finally, actually one before the last, right? We have this content analysis or repair tools, which as the name itself suggests, scans file systems for logical errors, lost clusters, and corrupted directories. And there could be one of two major types of errors that happen on a hard disk drive. There are soft bad sectors and hard bad sectors. Where soft bad sectors happen at a software level when there are bits that are corrupted as a result of some kind of infection or some kind of incomplete reader operation. Or you can also imagine that the other kind of bad sector that occurs is hard bad sectors, where due to some kind of physical damage, the sector gets damaged, right? It becomes damaged irreversibly, thereby making that sector or that block no longer usable. So therefore, disk content analysis tools will recover whatever files can be recovered from there and permanently close that portion of the hard disk drive block or sector from further read writes. You can imagine that there are hard bad sectors which result from hardware level damage to a hard disk drive sector or block, or even a track maybe. Soft bad sectors from software level corruption, like bits being overwritten in places that cause the file to get corrupt, or some kind of metadata-based problem, or some kind of incomplete file operation that led to the data being corrupt. Now, all of these things repair tools are able to manage, and it repairs file allocation tables and restores links between files and metadata if those links have been severed. And finally, it may log issues and suggest hardware diagnostics if physical disk failure is suspected. And what you see here is a very famous example of a disk content analysis tool called WinDIR Stat, which stands for Windows Directory Statistics. This is a software that helps you analyze the kinds of files that you have in your disk in a nice graphic. As you can see here, you can see that most of this guy's disk is made up of virtual disk files from maybe running a lot of virtual machines. But the rest are from application extensions, system files, and MP4 videos. So you can visualize and see which parts or which types of files are taking up more of your disk. That's about disk content analysis, and that's about disk repair tools. Finally, file compression software. These are there to reduce file size using algorithms like Huffman encoding or LZW. You can find out what LZW means. Maybe you can comment it under the comments as well. Or you can use algorithms like deflate as well. LSW stands for the names of the people that invented this file compression algorithm. So maybe you can find out what these names are, and those names would form the abbreviation. But again, you don't have to know about how these algorithms work. Just examples would be fine. And they reduce file size as a result, enabling faster transmission and reduce storage usage. It reduces the amount of storage used to store files and enables files to be transferred fast. And as a result, you can produce zip files, RAW files, and even GZ files. And finally, file compression can perform lossless compression, especially for text-based files, which result in no data loss, or lossy compression for multimedia to reduce quality slightly at a huge reduction in file size, especially JPEG, right? JPEG results in less discernible quality reduction, but a huge file size reduction. And actually, I think I said file compression was our last, but we do have backup software to look at as well. Backup software creates copies of files or directories or entire system images to external or cloud storage. It's about taking backups such that it enables disaster recovery or restoration of data in case of a corruption, deletion, or hardware failure. Right? It helps ensure that data is backed up in case of something goes wrong. And there are different backup strategies you can employ. There's full backups, incremental backups, and differential backups. Full backups are where the entire data set is backed up. Differential backup is only the alterations of data since the last full backup is to be backed up, right? Only the alterations or changes since the last full backup is backed up. And incremental backups are backups where alterations or additions since the last incremental backup are backed up. So you can imagine that these three are the major forms of backup strategies you have. And that, ladies and gentlemen, completes part 1 of System Software, Unit 5. If you have any questions, do let me know, and best of luck for your exams.